For our last comments on EDTA titration chemistry, we want to kind of put all these skills together and describe the whole thought process from a chemical standpoint that goes into an EDTA titration. Obviously, the data from EDTA titrations, when they're executed correctly, are stoichiometrically straightforward to interpret because the metal ion binds the coordinating ligand in a one-to-one fashion. So if you can locate your endpoint, you can use the basic stoichiometry of the equation to unravel the analyte's concentration. However, designing an EDTA titration is actually really complex because you have many different chemical factors that you have to consider holistically in order to make sure that your EDTA is in the right protonation state, your indicator will show the right color change, and your metal ion is soluble and available. So in this last EDTA module, we want to talk about how you can use everything you've learned that we've covered so far to design an EDTA titration if you need to, or to look at an EDTA titration procedure that someone else has designed and make sure that it's going to be appropriate for your needs. Because ultimately, EDTA is the primary classical method for assaying the concentration of a metal ion in a specific unknown. And accurately quantifying the concentration of metal ions is something that cross-cuts many different fields of laboratory science, from analytical chemistry to engineering to forensic science to environmental science to geoscience. Understanding what an EDTA titration is telling you and whether it's appropriate for the matrix and the analyte that you're looking at is essential to being a good laboratory scientist. Very few real-world laboratory procedures are a step-by-step series of instructions to follow, and as a researcher you can just step away and say, yep, I'm just going to follow the recipe and I'll get where I want to go in the end. It's what you don't appreciate about the chemistry that can come back to bite you, and so it's essential to understand where the thought process is coming from that led to the procedure that you're using, so that you know and you can guarantee as an analyst that the procedure will work and meet your needs. Because ultimately, whatever branch of science or medicine you're working in, once you have a job, the idea is this is now on me. I'm certifying my work. I understand the procedures I'm using. I understand the thought process that's going into my procedure. And ultimately, I'm going to be responsible for the work I'm doing. So it's essential to be able to take all the individual parts we talk about and understand how they fit together to make an effective procedure. The first thing to recall about an EDTA titration is that an EDTA titration is based on a complexation reaction between a Lewis acid, which is your metal cation or cations to be assayed, and the EDTA, which is a coordinating Lewis base. It's a ligand. So this metal ligand complexation is what allows you to quantify your analyte. However, in an EDTA titration, EDTA is not the only ligand present in the solution, and that's very important to understand to make sure that your titration is working effectively and you won't suffer from significant matrix effects. For instance, if you're working with a natural water sample, there may be other ligands in the solution like phosphate, or various amine species, or various conjugate bases of naturally occurring acids that can also complex your analyte and can potentially interfere with the EDTA. Even more challenging in terms of the experimental design is all of the indicators that we use to identify the endpoint of EDTA titrations are also ligands. They're also Lewis bases that coordinate to metals. Now, in general, the formation constants, the Kf value for EDTA, are significantly higher than they would be for any other Lewis base that's present in your reaction mixture, because EDTA is a hexadentate chelator. That means that the Kf values are going to be extremely large. But remember that the Kf values for EDTA vary, or I should say the K'F, the effective formation constants, vary at different pHs. And so depending on the pH at which you're running your titration, your EDTA may not be that much better a ligand for your metal than your indicator or any other Lewis base that's present in the mixture. So one thing to keep in mind is even if you have otherwise a perfectly clean matrix, you always have two ligands in an EDTA titration if you're trying to spot the endpoint using an indicator. You have the EDTA, which is a hexadentate ligand, and then you have the indicator itself, which undergoes a color change because it's also part of a complexation reaction with a metal. And in general, what happens in an EDTA titration is your metal is complexed by the original indicator molecule, which is then displaced by the EDTA in a ligand exchange reaction, forming your metal EDTA complex, and then the release of the ligand from the metal ion provokes a color change in the solution, which you can use to spot your endpoint. This is one reason why the color change in an EDTA titration is gradual, and you actually are looking for the loss of the original color to distinguish the endpoint of the titration. So the bottom line here is successful EDTA titration design is about understanding the interplay between the metal ion, the indicator, the buffer, and the chelator all at the same time. So first, let's take a look at the one part of the EDTA titration that we haven't discussed in detail yet, and then we'll show you how you can combine all these different chemical aspects of the titration into a single experimental procedure for quantifying the metal ion. So in order to achieve a successful EDTA titration, you of course need a metal ion indicator. A metal ion indicator is itself a Lewis base. It is a ligand which changes color when it binds to a metal ion. And when we discuss this today, we're going to go to areochrome black T as our kind of main example indicator, which is the indicator that we originally used to determine the total hard water content of our water sample in lab. The general reaction in an EDTA titration is not simply the metal ion binds to EDTA and you get the metal EDTA complex. Instead, it is the metal ion binds to the indicator, EDTA displaces the indicator ligand from its bond with the metal, forming the metal EDTA complex and kicking off the free indicator molecule, and this causes the indicator to undergo a color change. In our reaction with areochrome black T, the magnesium and the calcium EB complexes were red. But once EDTA displaced them and the indicator was released from the metal, the indicator by itself was blue. And as a result, in our hard water titration, we observed a red-blue color change, and the total loss of the red color indicated the endpoint of our titration, indicated that essentially all of the indicator had been knocked off the metal cation and was now floating free in solution. For a metal indicator to be useful then, it has to bind to the metal less strongly than EDTA does. And most of the time, that's not a big deal. The formation constants and the conditional formation constants between EDTA and the metal ion are massive, and the formation constants between the indicator and the metal ion are usually small to fair in terms of the value of the number. However, there are metals that are out there which bind to specific indicators very strongly, and so if you're using the indicator to visualize the endpoint of the titration, you have to be careful to choose an indicator that will work with the metal that you're using. If your indicator binds to the metal too strongly, EDTA can't displace it effectively, or at least can't displace it stoichiometrically or completely, and as a result, you don't get an obvious endpoint, and that eliminates your ability to effectively spot the endpoint in the titration. So while areochrome black T is a perfect indicator for calcium and magnesium between pH 9 and pH 10, there are several metal ions that are quite common that areochrome black T binds to too strongly to make it useful in an EDTA titration. Some of these ions include copper 2+, nickel 2+, cobalt 2+, and 3+, iron 3+, and several other ions. These D-block metal ions bind to areochrome black T very strongly. And therefore, even in the presence of a very good chelator like EDTA, the ions won't release areochrome black T and you won't get an obvious endpoint. In terms of the analytical language, in terms of the jargon, we refer to this as the metal ions blocking areochrome black, And this means that areochrome black, while it's a great indicator for quantifying calcium and magnesium, can't be used effectively to quantify copper 2+, nickel 2+, or any of these metals that bind it very strongly. So one thing you always have to consider when you're thinking about what indicator you're going to use in your EDTA titration, you have to make sure that it binds to the metal ion, but it binds weakly to the metal ion, and that EDTA will be able to displace the indicator stoichiometrically. Otherwise, you won't get a clean color change, and you won't be able to spot the endpoint just using a color change. You'll have to go to some other more sophisticated method for determining the endpoint of the titration. Maybe an electrochemical method using an electrode, something that we'll talk about in our next chapter. So cardinal rule is your indicator has to bind to the metal cation, but it can't bind too strongly or you won't get an obvious endpoint. And so this turns out to be really important because both your EDTA and your indicator are ligands for your metal. Also, both your indicator and your EDTA tend to be weak acids. We know that EDTA is a hexaprotic acid. There are 6 protons that can be deprotonated from the fully protonated EDTA molecule. And ideally, we want to run most of our titrations at a pH where the EDTA is either almost entirely deprotonated or is entirely deprotonated to maximize stoichiometric formation of our metal ligand complex. Our indicators also tend to be weak organic acids with pKa's of their own, and the pH of the solution influences the color of the indicator. So for instance, areochrome black tea, like most colored organic compounds, has an extended pi conjugation network. It has a lot of aromatic rings, which makes the overall molecule relatively rigid and minimizes the energy gap between the highest occupied molecular orbital and the lowest unoccupied molecular orbital. And as a result, it absorbs light in the visible region of the electromagnetic spectrum, and it has a color. So for instance, areochrome black tea has 3 acidic groups, one of which is shown as deprotonated in this structure right here. It has a sulfonate group, which has already been deprotonated in this structure, and it has 2 phenol groups, which, unlike an alcohol, are acidic groups and they have a pKa. The deprotonation state of the indicator molecule influences the energy gap between the HOMO and the LUMO in terms of the molecule's electronics, and controls what color the indicator is going to appear to the eye in solution. So for instance, if your areochrome black tea has a deprotonated sulfonate group, but protonated phenol groups, it is one color. If the sulfonate group is deprotonated and one of the phenol groups is deprotonated, it's a different color. If all of the acidic groups are deprotonated, it's yet another color. And so the pH of the titration also turns out to be important in terms of controlling the color that the indicator is going to show you, which again helps to make your endpoint as obvious as possible. In the case of areochrome black tea specifically, here are our acidic groups right here. So our sulfonate group, that's essentially already been deprotonated, so its proton is gone and it has a sodium +1 counterion instead. But both phenol groups can also be deprotonated. So when we're talking about the protonation state of the indicator and what color it's going to be, we use a similar kind of terminology. Remember, analytical chemists tend to be allergic to full organic chemical formulas and full organic structures. When talking about an indicator, like we use Y to represent EDTA, when talking about an indicator, analytical chemists just tend to call it IN to indicate the indicator. If we're showing areochrome black tea with 2 of its 3 ionizable groups still protonated, we refer to it then generally as the H2IN- form of areochrome black tea. The fully protonated form would be H3IN with no charge. If 2 protons are removed from our weak acid indicator molecule, we'd represent it as HIN2-, and if all 3 ionizable protons are removed, we would refer to it as IN3-. In the case of areochrome black tea, the H2IN- form has a red color in solution. The HIN2- form in solution has a blue color, and the IN3-, the fully deprotonated areochrome black tea indicator, has an orange color. Which areochrome black tea species we see in solution, of course, depends on the pH of the reaction mixture for the titration. The pKa of the deprotonation between the H2IN- species and the HIN2- species is 6.3. The pKa of the deprotonation between HIN2- and IN3- is 11.6. So in our laboratory work, where we're using areochrome black tea as the indicator in our hard water titration, at that pH, the vast majority of the areochrome black tea is in the HIN2- form. It's in the blue form, which is why our endpoint was indicated as a change in solution color from red to blue. Complicating this further, right, is we're just talking up here about the colors of the indicator when the metal ion isn't present. The indicator will give you a color whether the metal ion is there or not. Now, at our pH 9 to 10 in the EDTA titration we did, if the indicator is free in solution, it should be blue. However, whether the indicator is bound to a metal ion or not also influences its color. And so, for instance, if the indicator is forming a metal ligand complex with magnesium 2+, the magnesium and calcium complex ion that forms with the indicator is red. So even though the indicator by itself at pH 9 to 10 is blue, the metal ligand complex that it participates in is red. So we have these competing factors in terms of experimental design where we want to see an obvious color change. Red to blue is in general a nice, obvious red to blue color change, although there's obviously a learning curve, as we saw with looking at the color change associated with EDTA titrations. But the indicator is one color. The metal ligand complex of the indicator is another color. If, for instance, you were running your EDTA titration at too low a pH, like say pH 5, you would not see a color change because the protonated indicator is red and the metal ligand complex is red. So the pH has to be right in the titration for a whole variety of reasons. It's going to make sure the EDTA is in the right protonation state. It's going to make sure the indicator is in the right protonation state. And that's essential for you to see a color change to indicate your endpoint. And so ultimately what we see with these EDTA titration curves is, first and foremost, we need to carefully control the pH in an EDTA titration curve. Otherwise, a whole variety of side reactions can happen that will screw up the reaction that we're trying to perform. It's not like the EDTA metal complexation reaction is so robust that we can run it at any pH or under any conditions and see the color change that we want to see. So whenever you're designing an EDTA titration, or you're following a procedure that someone else has designed and said, hey, if you do this EDTA titration, you'll be able to quantify this metal analyte in your water sample, you have to carefully think through a whole host of factors to make sure the titration is actually going to work for you. And one of the most influential is the pH of the solution. And so if we think about this in terms of the EDTA titration curve, we have to think about two separate things simultaneously. The pH of the solution reflects the proton and the hydroxide concentrations in the solution, whereas the PM value reflects how much free metal ion is still in solution. And so if we think about the EDTA titration curve as a reflection of how much of the metal analyte we've locked up, this titration curve is only going to really look this way if we've chosen the right pH for our EDTA titration. So the pH of the solution is going to dictate three things that are key to the success of your EDTA titration. It's going to dictate the solubility of the metal ions, the speciation of the EDTA, and the speciation and hence the color of the indicator. So first and foremost, what do I mean by the solubility of metal ions? Well, metal ions, whether they tend to form soluble or insoluble complexes in water, when there are certain counterions there, metal ions tend to be more soluble at acidic pHs than they do at basic pHs. The reason for that is at more basic pHs, when you have metal ions, particularly relatively highly charged metal ions, like 2+ and 3+ cations, they can react with water and hydroxide to form insoluble metal hydroxides and metal oxides at high pHs. So for instance, if we're trying to run an EDTA titration and we're looking for calcium and magnesium, we have to be aware at high pHs, calcium will complex with hydroxide ligands to form a calcium hydroxide precipitate and be removed from solution, whether we have EDTA there or not. And if we have magnesium, magnesium will also precipitate in the presence of hydroxide ligands, forming magnesium hydroxide. So we have a competing equilibrium where the metal ions can react with hydroxide anions to form insoluble precipitates, removing them from solution and preventing us from using our usual straightforward interpretation of the stoichiometry. Now, at more acidic pHs, the concentration of hydroxide is low, and these equilibria lie to the right, and the metal ions stay unlocked and available for complexation by EDTA. Thus, we say metal ion solubility is higher at low pHs. Well, it seems like the obvious answer then is to run our EDTA titration at low pHs. But that's not going to work either, because the speciation of EDTA, which is a hexaprotic acid, we need the fully deprotonated form of EDTA, or close to it, to run an effective EDTA titration. Therefore, while our metal ions are going to be guaranteed to be soluble and unprecipitated at low pHs, EDTA is going to complex best at relatively high pHs, between pH 8 and 10. As a result, then, most EDTA titrations are buffered to a pH that's between 8, maybe 11, to run the reaction, which ensures that the pH is not high enough for you to precipitate out your metal ions as hydroxides, but it is high enough that the EDTA is mostly deprotonated and ready to perform the complexation reactions. So in our hard water titration, we buffered the solution with an ammonia-ammonium hydroxide buffer, raising the pH to about pH 9.5. High enough for the EDTA to be significantly deprotonated, but not high enough in the first week that either calcium or magnesium would precipitate as the insoluble hydroxide. So it'd still be in solution and available for binding to EDTA. This is where we use the conditional formation constant, because we know now how to make a projection, a quantitative projection, as to how strongly the ETA is going to bind the metal cation at a specific pH. So for instance, it's not until about a pH of 9 that Y4- truly becomes the most common species of EDTA in an aqueous solution. At pH 9, the alpha Y4- value is 0.30. At pH 10, it's higher still. So if we have buffered our EDTA titration solution to pH 9.5, that guarantees that pretty much all our EDTA will be in either the HY3- form or the Y4- form itself, which are our two forms of EDTA that will most effectively complex our metal ions. So in general, what we're saying about the pH of an EDTA titration solution then is it needs to be basic, but not too basic to be successful. Lastly, because that's probably not complicated enough, we have to consider what the color of the indicator is going to be at the pH where the EDTA is mostly deprotonated and the metal ion is still mostly soluble and available. And this is where we have to think about the pKa of the indicator as a weak acid and make sure we'll still be able to observe a color change when it goes from bound to the metal cation to released into solution. So lastly, we need to be aware of the pH of the solution when we set up an EDTA titration and consider whether at that pH are we actually going to see a color change between the indicator bound to the metal in solution and the indicator released from the metal in solution when the EDTA has complexed the metal. So generally when you're designing an EDTA titration, you choose the pH based on a pH that's low enough that there's no danger of the metal precipitating as the metal hydroxide, unless you want to remove one of the metals from solution like we did with magnesium in the second week of the EDTA titration. And you want to choose a pH where the EDTA is going to be either mostly in the HY3- form or the Y4-, the fully deprotonated form. And then you choose an indicator that will bind metal ions and show an actual color change between being bound to a metal ion and being released in the solution at the pH you chose. So our thought process in designing and executing the EDTA titration that went on behind the scenes was, we are going to choose a pH of about 9.5 for our total water hardness assay. That means our magnesium won't precipitate, our calcium won't precipitate, and most of our EDTA will be close to fully deprotonated, should make for a good EDTA titration. Now all we need to do is select an indicator that will show a color change when it's bound to calcium versus when it's free in solution. And this last decision sounds intimidating, but it's actually not that hard. In your textbook and in other reference materials, there's a list of indicators that will show a color change in an EDTA titration at specific pHs. And so if you look and say, I want to run the EDTA titration, it's going to be at a pH of 9.5. My analytes are going to be calcium and magnesium. You can essentially look in a list of possible indicators, and it will say, Arichrome black will work for calcium and magnesium. There are some metals it won't work for. It'll be blocked by at this pH, but it will work for calcium and magnesium. And so then, having chosen our indicator, we know that now it's a matter of technique and figuring out what the color of the endpoint looks like, and all the pieces are set up in place so that we'll have a stoichiometric reaction between the EDTA and the calcium and the magnesium, and we can figure out the total water hardness of our sample based on the endpoint or the equivalence volume that we identify in the titration when the solution changes from red, the indicator bound to our metal cations, to blue, the indicator released into solution because the EDTA has complexed our metal ions completely. And so that's the whole thought process that goes into the titrations design. And then when you have an established procedure, you can reap the rewards because you're saying, I want to know how much volume I have to add to get the color change to do this. In reality, to establish that procedure, a lot of chemistry had to be thought out behind the scenes, and then it's just written up stepwise, and there's your procedure. So I hope that in this last little segment, we just have shown you a little bit about what goes into an experimental design behind the scenes. When we come back on Wednesday, we're going to move on to a new topic. We're going to start talking about electrochem. So there's no post-lecture review questions that are focused on EDTA titration curve. Instead, what I want you guys to do is check out the worksheet that's posted behind this lecture, and it will start reviewing some of the electrochemistry concepts that you learned in Gen Chem 2 to tee you up for our discussion of electrochemistry as an analytical technique, which starts on Wednesday. So make sure to check that worksheet out. Go ahead and read the chapter 14 on electrochemistry basics in the new edition of Harris, and I will see you back here on Wednesday to start talking about electrochemistry.